All right, tonight we're going to talk about density. So this is, I'm sure, a familiar word. In fact, we used it on the second day of class. So I know you guys kind of are familiar with what it is. We're going to go a little more in depth because it's actually a really valuable piece of information about an element or about a substance. So what is density? You know the word, but what exactly does it mean? It's a very valuable piece of information. It's actually a combination of two physical features of a particular substance. It's its mass and its space. Really, another way to think about it is how much stuff per area. So let's think about it by comparing two different pieces of material. Let's compare a piece of wood to a piece of iron. All right, bear with me, I know my drawings aren't great here, but let's say we have a piece of wood, so it's in the sticks like a dowel rod, and then the same size piece of iron. So both of these objects are the exact same size. If they're the same size, that means their area, their volume is identical. Piece of wood, piece of iron, same size, same shape, so they have an identical volume. However, their masses won't be the same, so how much they weigh. The mass of the wood, if this is just typical wood, would end up being less than the mass of the iron. So why is that? If you have two things that are the exact same size, why would one weigh less than the other? This shouldn't be anything earth-shattering. Most of you know if you pick up a piece of wood, pick up a piece of iron, iron will be heavier. That is because the iron is more dense than the wood. That means there's more stuff packed into this piece of iron than there is this piece of wood. So the wood molecules, each one is lighter, they're spread more apart, and so you end up with less stuff per area. So inside of there, it's going to be, if we were to zoom in, a much smaller, less dense piece of wood. Whereas the iron, if we were to zoom in there, they would be very packed in. And so we'd end up with more stuff per area, and that more stuff creates more mass. Now here's a challenge question for you. If I were to take that piece of iron and I were to slash it in half, how would the density change? Well, if we cut it in half, its volume will be half, and so we divide the volume by 2. And so we would think the density would be roughly half as well, right? No, because if we cut it in half, we're losing half of that iron, and so the mass is also going to be divided by 2. That means the density won't change. Density is a constant for a substance. We can identify a substance based upon its density. So if we have a mystery metal and we find its density, we could look it up in a table and say, okay, well, that density tells me that piece of metal is aluminum or iron or silver or gold. Density is a constant. You change the volume, you're changing the mass as well, and so the density stays the same overall. So just like we can use color and smell and hardness, things like that to identify substances, we can also use the density to identify it. And that's why density is such a powerful thing, such an important thing. It's really easy to measure, and it's really easy to look up. Okay, so what are the units of density? Well, first off, we got to look at the equation for density. So density, which we'll symbolize with D, is equal to the mass divided by the volume. So mass is a measurement of stuff, how much stuff it has. Volume is a measure of area. And this tells us the stuff per area. So density is mass divided by volume. Now, we've learned about mass, volume, and length, and the units for that. And in this case, we have two different units. We have mass and we have volume. And each one, for mass, we can have multiple units, and for volume, we can have multiple units. So, for example, mass, it could be in grams, it could be in kilograms. If we were using the standard form, we would use pounds, things like that. So lots of different measurements for mass. Volume, there could be things like milliliters, identical to the milliliters, the cubic centimeter. You could have liters. So different choices for volume as well. Now, the units for density are what we call derived units. So it's all based on what we use for mass and volume. So let's say, for example, we have something, we're calculating its density. Its density is X grams, so like 5 grams or 4 grams. And its volume is Y liters. So what that means then, the units for our answer, density, is going to be grams divided by liters, and so the units would be grams divided by liters. So you just divide x and y and get grams per liter. So really the units can be any combination. If you have grams and liters, it would be grams per liter. If you had kilograms and cubic centimeters, it would be kilograms per cubic centimeter. If you had grams and milliliters, it would be grams per milliliter. So it can change. You can have all kinds of different combinations. To figure out the units, you just look at the numbers you started out with, the units you started out with. So really, you won't really need to ask, Mr. Jones, what's the units on this? You can just look at the equation and figure it out. And that's why these are called derived units, because they're units that are derived from the equation. So how do we measure density? Well, we need two pieces of information, since density is mass divided by volume. We would need both the mass and the volume, so we'd have to measure both of those independently and then combine them in the equation. Mass is easy. We use a scale, a digital one, triple beam balance, just something to get its weight, its mass. Volume, a little bit different though. We have a couple different choices there. First choice is water displacement. I know several of you guys are familiar with this because I saw you trying to do it during that past lab. So you start out with an empty graduated cylinder with water in it, then you drop an object inside of there, and what happens is, something that we observe a lot, that water level will go up. And then that difference between where it started and where it ended, we can visually look at, and that will tell us then the volume. Okay, so that's called the water displacement method. We look at the difference in the water level, that tells us the volume of that object. The other method is the overflow method. So you guys saw for the first time on that lab, a lot of you, the overflow can. So what that is you take a can, you fill it with water until the water level is right at the edge of that spout. You actually, what you want to do is fill it up, let it spill out, and once it stops spilling, you know it's right there on the edge. Then you gently take your object, you don't want to throw it in there because then you'll end up splashing, and you drop it to the bottom. And what happens is that takes up extra room, it causes some of the water to spill out, and you collect that water inside of an empty graduated cylinder. And so that water will collect, it'll fill up the graduated cylinder, and it'll give you a volume inside there. And then that volume would be the volume of this object. It's the same idea here, you're just displacing the water, but in this case you're spilling out the displaced water, catching it, and then reading its volume. And then the last thing you can do is if you have an object that's very evenly sized, nice straight sides on it, that you can measure with a ruler, you can go ahead and just measure its volume by doing the length times width times height rule. If you have an irregular shaped object like a sphere or just a chunk of something, you can't do this one. You're going to have to do one of these two. Volume is good if the object's small enough to fit in a graduated cylinder. If not, you have to do something larger like an overflow can. All right, let's practice together. So solid pure gold at room temperature has a density of 19.30 grams per milliliter. What would the volume of a 3-gram pure gold necklace be? So if we have 3 grams of pure gold, how much space would it take up? All right, this one's different because we are given the density right there, 19.30 grams per milliliter, and we are given the mass, 3 grams. That means we have this piece of information and this piece of information. And what we are looking for, the question is asking us what is the volume. And so we're trying to find this guy right here. So let's take the numbers that we have and let's plug them into the equation. So we have a 19.30 grams per milliliter for our density. And when you write equations, put the units on it. Even though we know what it is, write them on there anyway. You will thank yourself in the future if you just get in the habit. What, it takes you an extra second and a half out of your life to write them on there. So 19.30 grams per milliliter is our density, and that is equal to the mass divided by the volume. And we know that the mass is 3.00 grams, and our volume, it's unknown. So let's call it, just pretend this is math class, let's call it x. Okay? So we're trying to find that volume x, that unknown. Yes, this is algebra. Let's walk through it real quick in case you're kind of struggling on how to solve this. So we can imagine that as over 1, and then we can cross multiply. And so that means we're going to be left with 19.30 grams per milliliter times X equals 3 grams times 1, which would be 3 grams. Now if we want to solve so we can just get X, we're going to divide both sides by 19.30 grams per milliliter. Those cancel out. And then over here, grams will actually cancel out grams as well. So that we're left with the units of milliliters, which, hey, should make sense because we're looking for volume, and one of the measurements for volume is milliliters. Since we've canceled out the G's, we're left with mLs, and that makes sense then. So let's go ahead and solve this equation. When we divide 3 by 19.30, volume would equal 0.155 milliliters. So if we had 3 grams of a necklace, let's say it's a golden necklace, and we were to drop it in a graduated cylinder, the water level would rise by 0.155 milliliters. All right, here's another one. So a rectangular block of copper weighs 1,896 grams. The dimension of the block are 8.4 centimeters by 5.5 centimeters by 4.6 centimeters. From this data, what is the density of copper? So if you think you know how to do this, go ahead and pause it, give it a shot by yourself, and then resume it later. If you're kind of struggling, keep following along and I'll walk you through it. Alright, so we have its mass in grams. So we do know that. Let's start plugging numbers in. And now we need to find its volume. So here we have a regular shaped object with all even sides. It's a rectangle, and we have its dimensions right there. So we can find its volume by length times width times height. So when we multiply the length times width times height, we would find that the volume is 212.5, we'll round it to. So then what are the units on that? This is another example of derived units, since we are multiplying centimeters times centimeters times centimeters. That becomes centimeters cubed, and so that's the units of our volume. We can take that number and plug it into the bottom of our density equation, so 212.5 cubic centimeters. Okay, when we divide those two, we're going to get a density of 8.92. And the units, remember derived units, we're dividing grams by cubic centimeters, and so that means the units on this would be grams per cubic centimeter. Alright, that's it. That's the density of copper, and in fact, if you go onto Google and type in density of copper, you're going to pop up with this number right here because it's constant. Okay, if we had a bigger chunk of copper or a smaller chunk of copper, we would do the calculation and we would still come up with 8.92 grams per cubic centimeter. So just follow the units, mass divided by volume, and you've got your answer.